This is the explainer that corresponds to the topic random variables and probability. So regarding the issue of what is probability, then you need to remember the two conceptions of probability, which are the frequentist, sometimes called the objectivist, which says that probability is the long-run expected frequency of the occurrence of an event. So basically, the model, or the best metaphor for this, is to toss a coin several times, and then the expected frequency of heads is 50%, and that would be the probability of that event. But for the Bayesian, or sometimes called subjectivist, probability is a degree of credence on the occurrence of an event. And to me, the Bayesian conception of probability is more flexible because you can assign probability to many things, many events, almost anything. You don't need to have the requirement that the event needs to be repeated on time. So these are the main issues in the conception of what is probability. Random variables. Main issue here is the differentiation between the concept of probability of variable in research and science and the concept of variable in probability theory. So in research and science, a variable is a characteristic of something that can take many values. In probability theory, a variable is a random variable and is the outcome of an experiment. But by experiment, we mean not the type of experiments we run in science, but a random process, which could be tossing a coin, rolling a die, or playing the roulette, or observing a drone landing in a city. So these are it's very important that in some cases when we do research, we use the concept of variable without differentiating these two conceptions, and that's okay because we are using the random variables of probability theory to analyze data. But we need sometimes to clarify that we are referring to the random variables of probability theory or to the type of variable in research. So we will see that in some circumstances which is important to make the differentiation. Okay, so this is the example of the city that we went through in the master class. So in this explainer, I'm going to ask a number of questions, and the idea is that you try to answer the questions by yourself or with a group of peers, and then so pause the video, try to answer the questions, come back and see if your questions match the answers I provide. Sorry, if your answers match the ones I provide. So here is the city with region A with 400,000 people, region B 300,000 people, region C 200,000 people, and region D 100,000 people. So 40% of people live in region A, 30% in region B, 20% in region C, and 10% in region D. So the question is, what is the sample space of this experiment? So try to answer and come back. So the sample space here is the set of all the possible outcomes. What are the possible outcomes? A, B, C, or D. So that's the sample space. So to formalize, we say that it's a set, and the set contains the elements, and the elements are A, B, C, and D. And that's it. That's all. It's not a very complex concept. Okay, so second question. Mention possible events in this sample space. Okay, try to answer the question. Come back. Now, possible events are combinations of outcomes. So, or it could be any subset of that set of possible outcomes. So instead of being just A, or just A is an event. What's the probability that the drone lands in A? Well, A in that case would be one event. Or B is also an event. C is an event, D is an event. But we can combine outcomes. So there are events that are combinations of outcomes. So we can define, for example, an event called west. And west is if the drone lands in A or B. Or east. And east is, the event east is that the drone lands in C or D. Or center. Center means that the drone will land in B or C. Or periphery, and that's that the drone will land in A or D. And we can combine three regions. We don't give it a name, we give it a letter, P. And P is that the drone will land in A, B, or C. Okay, so events are combinations of the outcomes. Next question. Define a random variable for this experiment. And here comes the concept of random variable. So I'm going to release some of the constraints that I put in the masterclass. So in probability theory, people are very particular about random variables being numbers. So the values of the random variables should be numbers. And that's why we went through the sometimes a bit redundant process of transforming the values A, B, C, and D into 0, 1, 2, and 3. So the random variable x is 0 if the drone lands in A, 1 if the drone lands in B, 2 if the drone lands in C, and 3 if the drone lands in D. So the random variable can take these 4 possible values, and they are numerical. So we can define a random variable that doesn't match the elementary outcomes in this process. We can define a random variable as random variable Q is 0 if the drone lands in A or B. And random variable Q is 1 if the drone lands in C or D. So basically, when we define a random variable, we can go beyond the possible outcomes. So that's why we make this differentiation. But sometimes we use the outcomes are what we are interested in, not a combination of outcomes. So it seems a bit redundant to define a random variable after defining the possible outcomes. Okay, so now let's do some probabilities. So basically I'm asking, what are the following probabilities? What's the probability that x equals 0? What's the probability that x equals 1? What's the probability that x equals 2? What's the probability that x equals 3? What's the probability that x equals 0 or 1? What's the probability that x equals 0 or 3? What's the probability of x being 1 or 3? And what's the probability of x being equal to 0 or 1 or 2 or 3? So pause the video and try to answer these questions. So, what's the probability of x equals 0, or the drone landing in the region A? It's 0.4, because there are 40% of people living in that area. Probability of x equals 1 is 0.3, probability of x equals 2, 0.2, probability of x equals 3, 0.1. Okay, so they combine possible outcomes. What's the probability of x being 0 or 1? Well, we need to add the probability of being 0 plus the probability of being 1. 0.4 plus 0.3 equals 0.7. Next, what's the probability of x being 0 or 3? So the probability of being in 0 is 0.4, and the landing in 3 is 0.1. So 0.4 plus 0.1 is 0.5. Next, probability of x being 1 or 3. probability of the drone landing in 1 is 0.3, and probability of the x variable to take the value 3 is 0.1. So 0.3 plus 0.1 equals 0.4. And finally, what's the probability of x takes the value 0 or 1 or 2 or 3? Well, basically, it is that the drone will land somewhere in the city, and that is 1, because it will certainly land in one of the regions. Okay, now we add a new characteristic. So we've got whether the drone lands in regions A, B, C, or D, which we replace by a random variable that takes values 0, 1, 2, 3, and whether it lands in an inland or a coastal area. So we've got here same example as in the masterclass in omega 1, which is inland and 0, 100,000 people, inland coastal and 0 is 300,000 people. Omega 3 is inland and 1, which is 100,000 people. Omega 4 is coastal and 1, 200,000 people. Omega 5 is inland and 2, 150,000 people. Omega 6 is coastal and 2, which is 50,000 people. Omega 7, inland and 3, 50,000 people. And omega 8 is coastal and 3 and 50,000 people. So the random variable x is what we've done before. We assign 0 if drone lands in A, 1 if in B, 2 if C, 3 in D. And random variable y is 0 if drone lands in inland, and is 1 if it lands in a coastal region. Okay, so the questions here are first the non-conditional probabilities, so what probabilities we've been going through so far. What's the probability of x equals 0, probability of x equals 1, probability of x equals 2, and probability of x equals 3. That's regarding region. And then what's the probability of y equals 0, which is what's the probability of y landing in inland, and probability of y equals 1, which is the probability of drone landing in coastal. So probability of x equals 0, we've been through that before, is 0.4. Probability of x equals 1 is 0.3. Probability of x equals 2 is 0.2. And probability of x equals 3 is 0.1. Now, what's the probability of y equals 0? Well, that's the probability of the drone landed in any of the inland regions. So we need to add the probabilities for omega 1, omega 3, omega 5, and omega 7. So omega 1 is 0.1, omega 3 is 0.1, omega 5 is 0.15, and omega 7 0.05. Adding these values, we get 0.4. And what's the probability of y equals 1? Well, we can add omega 2, omega 4, omega 6, and omega 8, and so the probabilities corresponding to those outcomes, and it would be 0.6. We can also, because these are two events that are mutually exclusive, that means that if one event occurs, the other doesn't occur, and also both events cover all the possibilities, so all the outcomes. That means that if that's the case, we can do 1 minus the probability of the other event to calculate this probability. So we can get 0.6 by adding the corresponding omegas, or we can get 0.6 by doing 1 minus 0.4 because we obtained the probability of y equals 0 before. So that now gets complicated because we are going to deal with the conditional probabilities. And I do research in conditional probabilities to try to help people to do well with this, because we humans are really bad. So let's go slowly. And remember, conditional probability is the probability of an event given that another event has occurred. Okay, so we've got the number of populations per region here, which is the same as before. And these are the questions. What's the probability of x equals 0? So what's the probability that drone lands in the region 0 or region A? Given that y equals 1. This is given that we know that the drone landed in a coastal area. So given that it landed in a coastal area, what's the probability of the drone landing in the 0 region or the A region? Okay, so we have to do that for each of these 8 possibilities. Okay, how do we do that? So, when we've got that, we know that y equals 1, that reduces the sample space. So, because this new information that we know for certain that the drone landed in a coastal area, then we need to ignore the inland area. And now our sample space is reduced. Now, before it had 8 possible regions. When we know that an event occurred, the event that the drone landed in a coastal region, now we have only 4 possible outcomes. So the sample space reduced, and the total probability has to be reassigned. So how do we do that? Now, the total population now, instead of being 1 million people, is going to be 600,000 people, because omega 2, the population in omega 2 plus the population in omega 4 plus the population in omega 6 and the population in omega 8, that's 600,000. Okay? Because the probability of landing in coastal area was 0.6. So, given that we know it landed in coastal area, now what's the probability that it landed in the region 0 or region A? Well, that's the probability for omega 2 over the probability for all the coastal areas. So the probability for omega 2 is 300,000 or 0.3, and we divide 0.3 by 0.6, and that's 0.5. Okay, so answer of the first question is 0.5. So basically, if you see all these blue bars, and you put all these blue bars one on top of each other, and you will see that omega 2 occupies half of the space. So it makes sense that the probability is 50%. Now, let's go here. Probability of x equals 1, given that we know that y equals 1. So that's same as before, but instead of doing omega 2 divided by 0.6, we do omega 4 divided by 0.6, or the probability given to omega 4. So that is 0.2 divided by 0.6, and that's 0.333, or 1/3. And so that's the probability of x equals 1, given that y equals 1. Now, for the third, probability of x equals 2 given y equals 1, then we have to do omega 6, the probability for omega 6 divided by the probability for omega 2, omega 4, omega 6, and omega 8. So omega 6 is 0.05 divided by 0.6. That gives us 0.0833. And for the last one is exactly the same. Probability of x equals 3 given that y equals 1. So we do the probability for omega 8, which is also 0.05 divided by 0.6. And that's, again, 0.0833. Now, let's go to the second column. Probability of x equals 0 given that y equals 0. So now, the event that occurred is that the drone landed in an inland area, so in one of the yellow regions. And we know that the probability of landing in one of these regions is 0.4 because there are 400,000 people in the inland regions. So now that we know that it landed in a yellow region or in an inland region, we ignore the blue bars. Okay? So basically this question is asking how big is omega 1 in comparison with the sum of the 4 omegas. Okay, so omega 1 is 0.1 and the sum of the 4 omegas is 0.4. So that's 25%. So the second one, probability of x equals 1 given y equals 0. So that's omega 3 over the sum of the 4 omegas. So that's the same as before. 0.1 divided by 0.4, and that's 0.25. Now, third, probability of x equals 2 given that y equals 0. So what's the probability that lands in region 2 given that we know it landed in an inland area, and that's the probability for omega 5 over the sum of the probabilities of the omega 1, omega 3, omega 5, and omega 7. And so that's 0.15 over 0.4. That gives us 0.375. Finally, the probability of x equals 3 given y equals 0. So the probability that it landed in region 3 given that we know it landed in an inland area. So that would be the probability for omega 7 over the probability of the sum of the probabilities of omega 7, omega 5, omega 3, and omega 1. So that's 0.05 over 0.4. And that is 0.125. So if we add the 4 probabilities, 0.25 plus 0.25 plus 0.375 plus 0.125, that's again 1. So if we add these 4 probabilities, they add to 1. And if we add these 4 probabilities, it adds to 1 as well. Now, this is also conditional probabilities, but the other way around. So the event that we know is that it landed in one of the geographical regions. And based on that, we have to determine the probability of landing in inland or coastal. So probability of y equals 0 given that x equals 0. So we know that x landed in 0, so it landed in this area. So now the sample space is reduced to 2 possible outcomes. It's either omega 1 or omega 2, because we know it landed here. It didn't land in the other areas. So what's the probability of y equals 0, which is inland, given that it landed in region 0? Well, that's omega 1 over the sum of omega 1 and omega 2. We know that the sum of omega 1 and omega 2 is 0.4, and omega 1 is 0.1. So 0.1 over 0.4 is 0.25, or 1/4. Okay. Now, if we go, instead of going down, like we did before, we go horizontal, we keep in the same line, then these two probabilities should add to 1. So if this one is 0.25 or 1/4, this one should be 0.75 or 3/4. Why? Because we know the drone landed in region 0, so what's the probability of landing in coastal? So this omega 2 is 0.3 divided by 0.4, which is 0.75. Let's go to the second line. Probability of y equals 0 given that x equals 1. So we know that the drone landed in region 1. So what's the probability it landed in an inland area? So that's the probability for omega 3 over the probability for the sum of omega 3 and omega 4. So the sum of omega 3 and omega 4 is 0.3, and the probability for omega 3 is 0.1. So 0.1 over 0.3 equals 0.333. And if this is 0.333, then probability of y equals 1, given that x equals 1, should be 0.6666, which we can check by doing the probability for omega 4 over the probability for the whole region 1, or the sum of the probabilities of omega 4 and omega 3. Okay, let's go to the third line. Probability of y equals 0 given that x equals 2. So we know now that the drone landed in this region, region 2. So what's the probability that it landed in an inland area? Well, that's the probability for omega 5 divided by the probability for the whole region. So probability for omega 5 is 0.15, and the probability for the whole region is 0.2. So that gives us 0.75. And if we continue here, this should be 0.25, because it's omega 6, probability for omega 6, which is 0.05 over the probability for the whole region, which is 0.2. And finally, probability of y equals 0 given that x equals 3. So we know it landed in this area. What's the probability that it landed in an inland? Well, you can see that the two bars are the same size, so it has to be 50%. So we can check by knowing that the probability for omega 7 is 0.05, and the probability for omega 8 is also 0.05. So the sum of these two is 0.1, and if we do omega 7 divided by probability for omega 7, 0.05, divided by the probability for region 3, which is 0.1, is 0.5. So a probability of y equals 0 given x equals 3 is 0.5, and so is the probability of y equals 1 given that x equals 3. Now we are expanding on number of landings, and let's consider a city in which the populations in the two regions are the same. So the probability of landing in A is 0.5 and the probability of landing in B is 0.5. Similar to tossing a coin. Okay, and we are doing 3 Bernoulli experiments. So Bernoulli, remember that Bernoulli distribution is just one landing. And we call Bernoulli experiments of doing more landings. So each of the landing is one experiment. So after 3 Bernoulli experiments, then we have 4 possibilities. We define the random variable x as x equals 0 if 0 landings are in area A, x equals 1 if 1 landing is in area A, x equals 2 if 2 landings in area A, and x equals 3 if 3 landings are in area A. So in order to calculate those probabilities, it's not the population only doesn't help. We also need to do some multiplications. Okay. So if we see the sample space here, it takes into account the 3 landings. That the first possibility is the first landing, the second letter is the second landing, and the third letter the third landing. So in this case, we call omega 1 the sample space in which, the outcome in which the 3 landings are in A. Omega 2, the first 2 landings in A and the third in B. Omega 3, first landing in A, second in B, third in A. Omega 4, first in A, second B, and third in B, and so on and so forth. Omega 8 is that the 3 landings are in B. So, what's the probability of x equals 0? And remember, x equals 0 means that are 0 landings in area A after 3 Bernoulli experiments. Probability of x equals 1 is that 1 landing in A, probability of x equals 2, probability of 2 landings in A, probability of x equals 3 is probability of 3 landings in A. Okay, 0 landings in A, we are looking at omega 8. So, what's the probability that the drone will land in B? Well, this one is easy, 0.5. What's the probability that lands in B? Again, 0.5. What's the probability that lands in B? 0.5. So this one is 0.5 times 0.5 times 0.5. So let's see the results here. So I will return to this slide. So as I show you, 0.5 times 0.5 times 0.5 is 0.125. Okay. So probability of x equals 1. So that means only 1 landing in area A after 3. So we have 3 possibilities, 3 outcomes of this sample space belong to the event x equals 1. So we have omega 4 here has only 1A, omega 6 has only 1A, and omega 7 has only 1A. So 3 possibilities. Now, it's very easy because what's the probability of landing in A and what's the probability of landing in B? Is the same. It's always 0.5. So we've got, as before, probability of 0.5 times 0.5 times 0.5. But because this occurs in 3 outcomes, then we multiply that by 3. And that gives us 0.375. Now, I was going to return to the previous slide, but I don't think we need it because probability of x equals 2 means probability of 2 landings in area A, and we can find this here. So we've got omega 4 has 2 landings in B. Sorry, 2 landings in A. So omega 2 has 2 landings in A. And omega 3 has 2 landings in A. And omega 5 has 2 landings in A. So again, 3 outcomes belong to this event of 2 landings in area A. So, well, we do the same as before. It's exactly the same because 3 probabilities are always 0.5. So we do 0.5 times 0.5 times 0.5. And because there are 3 cases in this case as well, in this event as well, so we multiply by 3, so we get the same, 0.375. And finally, what's the probability of having 3 landings in A? Well, we have to look at omega 1 only. So omega 1 only has the 3 landings in A, and the probability of landing in A is 0.5 times 0.5 times 0.5. So the probability of 3 landings in A is 0.125. So binomial distribution comes from a Bernoulli distribution with parameter 0.5. Then the distribution becomes symmetrical. So you can see that the central values 1 and 2 has the same probability, and it goes down when you go to the extreme lower value, and it goes down when you go to the extreme highest value. We are going to return to this one. I'm going to ask you for an example that is a bit more difficult. It's actually the same example as the masterclass, but I want you to do it yourself. So, distributions, that's what we are going to do that. Remember, that's the Bernoulli distribution in which we are interested in the parameter, and we take the x, which is the random variable, takes the value 0 and 1, but typically they are called 0 is called failure and 1 is called success. So that's it. That's the only parameter we need for the Bernoulli distribution. But when we expand to a binomial distribution that we do a lot, then here we need two parameters. Pi is 0.20, which is the same as in the Bernoulli that we've just seen, and n equals 3, which it means that will be 3 experiments or 3 drone landings. Okay, so basically this question is the same. Probability of x equals 0, probability of x equals 1, probability of x equals 2, and probability of x equals 3. And the sum of these probabilities should be 1. Okay, so try to do it yourself, and is the example in the masterclass. So, we do the explanation without looking at the omegas now. Probability of x equals 0. Well, remember that the probability of, that means that there is 0 successes. So it never lands in 1, it always lands in 0. And there's only one case in which that happens. Now, unlike in the previous example that all the probabilities were always 0.5, here we have some probabilities are 0.8 and some probabilities are 0.2. So in this case, probability of landing in 0 is 0.8, which is 1 minus 0.2, which is our pi. And so we need to multiply these three probabilities, 0.8 times 0.8 and 0.8, and that's 0.512, which is here, is represented here. Now, what's the probability of x equal 1? And you can see probability of x equal 1 and x equal 2 is probability that there is one landing in region 1, or there is one successful experiment. Probability of x equals 2 means probability that there is going to be 2 landings in the region 1, or that there are 2 successful experiments. And we saw before that there are three possible outcomes that belong to this event, and 3 possible outcomes to this event. So this is the same, 3 times whatever comes next. And what comes next? Well, 0.2 is the probability that we will have a successful event, successful experiment, and 0.8 is that is unsuccessful. So successful experiment times the probability for an unsuccessful experiment or failure, and times for the probability for another unsuccessful experiment. And remember that there were three outcomes, 3 possible outcomes that belong to this event. So 0.2 times 0.8 and 0.8 times 3 is 0.384. So you can see that if the bulk of the distribution is in 0 and 1, 2 and 3 landings in or successful experiments are very unlikely. Well, why? Because we started with a very low probability for one experiment, and when you multiply those probabilities, it becomes lower for higher values in this binomial distribution. So the last, so probability of x equals 2, that means is that there will be 2 successful landings. So we have 2 0.2s and 1 0.8, and then we multiply by 3 because there are 3 cases in which this could happen. And that's 0.096. It's shown here at almost 10% or almost 0.1. And probability of 3 successful experiments or 3 landings in region 1, well, that's very unlikely because the probability for the first one to land in 1 is 0.2, then you multiply by 0.2 again, and we multiply by 0.2 again, and that's this number, 0.008, so less than 1%. Our final distribution is the beta distribution. The beta distribution has 2 parameters, A and B, or alpha and beta. And in the one shown in the graph is A equals 2 and B equals 2. So remember that the beta distribution is almost the inverse of the Bernoulli. So in the Bernoulli, we know if we take the drone delivery metaphor, we know the population of the cities. We know that there is 20%, or in one example is 20%, in another example we use 50%. Let's say 50%. If pi is 0.5, that means that we know that the population in region 1 is 0.5 and the population in region 0 is 0.5. Or we know that the probability of having a successful trial is 0.5 and the probability of a failure is 0.5. The beta distribution is the other way around. The parameters A and B sort of tell us how many successful and unsuccessful trials were there. And the value, the x, the random variable x, tells us what's the population in the city, or what's the probability of success. Okay? So, take into account this one. We've got sort of 2 landings in region 1 and 2 landings in region 0, or 2 successful trials and 2 unsuccessful trials. Well, this is not enough information to be very confident, but based on this, we've got 2 and 2, the most likely value is 0.5, but still, it could be the case that the population is much larger in one region than in another. So that's why this distribution is very, very spread. So you can see that, yeah, 0.5 is the most probable value, but still values like 0.2 or 0.1 have a decent probability. Probability of 0 and 1 is 0 because at least we have 2 landings in each, so it cannot be 100% of the population could be in one region or in the other. So let's see the questions. Which values would be more probable with the following parameters? A equals 100 and B equals 100. So basically, this is saying, what's the probability of having a successful trial, a successful Bernoulli trial? Or what's the probability or what's the population? What's the proportion of the population in region 1? Well, A and B are telling us that there were 100 successful trials and 100 unsuccessful trials. So, even though it's still not definite, it gives us an idea that the populations in the 2 regions are very similar, because we are observing the same number of landings in each region, or it's telling us that the probability of the one Bernoulli trial is 0.5, because we've got 100 successful, 100 unsuccessful. Still not definite, so the most probable value will be 0.5, but values close to 0.5 are still likely as well. But you go to 0.4 and 0.6, it's becoming less and less likely. And 0.7 onwards, or 0.3 or less, it's very, very unlikely. Okay, so that's the first case. Second case, A equals 10 and B equals 90. So this is very different because we've got a very different number of landings in one region than in the other. or only 10 successful trials and 90 failures. So this is telling us that the populations are different in each of the cities, or in probability, formal probability, that they are only the probability of successful trial is much lower than an unsuccessful trial or a failure. Well, actually, what's the actual value? Well, you need to consider that of 100 trials, 10 were successful and 90 unsuccessful. So that's like 0.1 or 10%. So the most probable value in this beta distribution would be 0.1. So we will have a distribution with higher probabilities of 0.1 and then going down. Now, third case is the opposite. A equals 90 and B equals 10. So this is telling us that we observed 90 successful trials and only 10 failures. So that's exactly the opposite. What's the most likely value? What's the most likely probability of a Bernoulli trial? 90%, because we've got 90 over 100. That's 90% or 0.9. So we'll have a distribution that peaks over 0.9. And the final one, we've got A equals 50 and B equals 150. So that is a case in which of 200 trials, 50 were successful and 150 were unsuccessful. So what's the most probable value is 50 over 200. And here we've got all the answers. So in this case it's 0.25. Okay, so this is the beta distribution, and this is the last distribution and the end of this explainer.